as we get started, let me quickly review over the circle. I know we took a quiz over it in our last lesson, but a circle, what's its definition? Quentin?
It's a locus of points at given distance from a given point.
Perfect. The locus of points, that's every definition is going to start with the locus of points, right? It's the locus of points, a given distance from a given point. The given distance class is called the radius, and the given point is called the center. What is the conic form of a circle going to look like, Jamie?
A.
Well, any conic, yes, but a circle specifically.
X minus x squared.
The conic form. Help her, Quentin.
R squared equals.
All right, what I'm going for is x squared plus y squared plus ax plus by plus c equals 0. All right, this is the conic form of a circle where you've got a 1x squared and a positive 1y squared. That's right here. This is what defines circle happening. And if we didn't have ones, we would divide everything, wouldn't we, to get those ones. That's circle. Now, the circle form, of course, Jamie, is
X minus x squared plus y minus y squared equals y squared.
and that way we can see the center and we can see the radius, right? But the conic form is going to be x squared plus y squared, the ax, by plus c equals 0. What is the eccentricity of a circle? Quentin? 0. There's nothing eccentric about it. And there's really no way even to define the eccentricity. Some people have said, I've actually used this definition myself in the past, the distance of the center from the center. Obviously that's 0, right? You'll find out why I could define it that way when we talk about the ellipse. For instance, from physics, you remember an ellipse has 2 focal points. The closer they get together, the closer it gets to a circle, and the closer the eccentricity gets to 0. Well, if those 2 points were to lie on top of each other, you get a perfect circle eccentricity 0. So, but really, I mean, how do you define distance from the center from it? It's kind of an awkward definition, admittedly. The eccentricity is 0. Then we got yesterday to a new conic, and that was the parabola. How did we define the parabola, Jamie?
Sure.
You know the first few words.
The locus of points.
The locus of points.
A given distance from a line and a given point.
Careful, not a given distance from a line and a given point, but
Equal.
so, what's the word I'm looking for, Quentin? Equidistant from a given line and a given point. Because the locus of points equidistant from a given line and given point. What do we call that given line, class? Directrix. Hey, we remembered how to pronounce it today. Directrix. Good. And then what do we call the given point, Jamie?
The focal point.
The focal point, or the focus, right? Focal point is how we refer to it in physics with our mirrors, and then so in pre-calculus, the focus is what we call it for those watching on YouTube. If you're not taking physics at the same time you're taking pre-cal, you will not understand the struggle. But we're talking about parabolic reflectors yesterday in physics, and we're talking about parabolas here, so there's a lot to keep up with there. So with our parabola, remember, we've got, let's just say the parabola looks something like this. We've got this point that is our focus. We've got this line that is our directrix. And then we've got this point that is where the parabola changes direction. I don't know that this is well drawn, actually. I think maybe the point would be more here, which means the line would actually be more like this. So ignore the initial drawing. So actually, I don't think that's where it changes direction. This point where the parabola changes direction is called, class, the vertex, and that is a matching term from physics. The vertex, so we have our focus, we have our vertex, we have our directrix, and if I were to draw a line through the focus, through the vertex, it would actually be perpendicular to the directrix. What do we call this line? In this class, we call it the axis of symmetry. With mirrors, we call it the principal axis. I know, it's just, head exploding here. The axis of symmetry, and then perpendicular to the axis of symmetry. Right here through the focus, we have a very important focal chord, our right angle focal chord, and it's called the, well, this is the focal length, right? From V to F is the focal length, but this perpendicular through the focus. The lattice rectum, the right angle line that goes through the focus. And this is what helps us to get the proper curvature. And remember we said yesterday, now we're not going to use the term aperture in this class, right? But how wide the parabola is affected by the length of the lattice rectum. Small lattice rectum, tight parabola. Long lattice rectum, very wide parabola. Okay? And so all of this, what does the conic form of a parabola look like? It doesn't look exactly like this. What is the conic form of the parabola going to be? Quentin?
X or y squared equals 4p.
Not the parabolic form, the conic form still. Looks a lot like the circle, but it's not x squared plus y squared, it's x squared or y squared. Plus ax plus by plus c equals 0. So again, just from the conic form, you'll be able to tell the difference. If you have both of them, both squared, both ones, both added, circle. You have only one of them squared, and then of course everything else, that's your parabola. Do you see the difference? But you're still going to want a 1x squared or a 1y squared like we did with the circle. Now the parabolic form is what Quentin was starting to tell us a second ago, Jamie. There's actually two different parabolic forms depending on whether the parabola goes up, down, or side to side.
It's like 4p.
There is a 4p in it. Quentin. Y squared equals 4px, or either of you.
X squared equals 4p.
There we go. Either one of these forms is our parabolic form. Maybe the p is for parabolic. Remember yesterday we were like, why p? Because what does the p actually represent? Nothing that has the letter P in it. Focal length. And for that matter, what does the absolute value of 4P represent? Jamie? Quentin? The length of the lattice rectum. Okay, so the number that is here, the coefficient of the first power variable, is your the length of the lattice rectum. Now, we tend to think of it in two halves, right? Because the lattice rectum is bisected by the axis of symmetry. So what I like to think of is I like to think of double the focal length, or half the 4p, 2p, as each side of the lattice rectum. So 2p here and 2p here. Technically absolute value, right? Because it's same on both sides. And of course, P itself is right here, that focal length from V to F. By the way, here from P, or from V to the directrix would be the opposite, the negative of P, wouldn't it? Okay. We said for our purposes, for now, the vertex is always simply going to be at 0, 0, the origin, though today we're going to start changing that. We'll show you how we account for that. Also, how do I know whether it's up, down, or side, side? How do I know which axis is the axis of symmetry? Whether it's supposed to be the x-axis or the y-axis, Jamie?
The one that's not square.
The one that's not square. So here would be x-axis of symmetry. Here would be the y is the axis of symmetry. And then finally, the eccentricity. We said a circle's eccentricity is always 0. A parabola's eccentricity is also constant. It's always 1. But how do we arrive at that? 0 is a challenge to arrive at, a challenge to define for obvious reasons. 1 is not. 1 is a ratio of two distances. What two distances get compared to each other in the eccentricity, Quentin? And it's kind of in the locus, if you will.
The directrix and the vertex.
Remember, what's the definition of a parabola? It's the locus of points that are equidistant from a given point, called the focus, and a given line, called the directrix. So the distance of any point, let's just take this point for instance. However far it is from the directrix, and however far it is from the focus, these two distances have to be the same. So distance to focus compared to distance to directrix. Again, this is for any point in the curve. That, because they're always going to be equal, their ratio always becomes 1. So that's kind of a review of what we did yesterday. Okay, and let's go ahead and take a look at the homework that you had yesterday. Good news is we don't have a quiz today, so we were a little, it was a lot of information to digest, admittedly, yesterday. So hopefully as we review, do some more review in our next lesson as well, that'll help us to retain a lot of these facts and information. Let's take a look at the homework now. And we had two parabolas that I was asking you to graph. The first was y squared equals negative 8x. And let me set up a Cartesian plane here very quickly. You've got your homework out. Ready to check here as soon as I am ready with the grid. That's a sloppy 9, looks like a 7. All right, and there we go, excellent. All right, so the first things first, there are 4 things we're going to analyze. For now, and again, this is going to change very soon, we need to figure out where the vertex is. But again, for our purposes, the vertex is going to be 0, 0. Again, it's about to change, but for now, 0, 0. Then we need to know which axis is the axis of symmetry. Is this going up, down, or is it going side to side, class? X. So it's going x-axis of symmetry, side to side, right? It's going one side or the other. The next thing we need to determine is the focal length. Remember, the focal length is represented by the letter P. But this is not P. That is 4P. So what is P? Negative 2. And then finally, we need to know the length of each side of the lattice rectum. And for that, we simply double this or cut that in half. 4. Or you could just say, well, I know the whole thing's 8. By the way, not negative, right? You can't have negative length per se. You don't have negative direction of movement, not so much negative length. So 4 is each side of the lattice rectum. What we should have had for a graph then was, check your work, 0, 0 origin, vertex. On the x-axis going negative 2 gets you to your focal point. By the way, negative 2 to the focus, positive 2 to the directrix. And then through the focus, perpendicular to my x-axis of symmetry, parallel to the directrix, up 4, down 4 to the end points of the lattice rectum. You don't have to draw the lattice rectum. But we'll curve our way through here and through there. And we should get a parabola that looks something like that. How did we do on the first one?
I had negative 2 2/3 for my focal length.
Oh my.
5 1/3 for my lattice rectum.
So you try to divide by a 3 instead of a 4, perhaps? All right, does it make sense now? All right, and let's take a look at the other one that you graphed. And that was x squared equals 2y. Vertex, class? 0, 0. Axis of symmetry, the y-axis. Focal length, 1/2. Very good. And then each side of the lattice rectum, 1. The whole lattice rectum is only 2, so this is a narrow parabola. Each side is only 1. So we're going to put our vertex here at 0, 0 on top of the other vertex. But on the y-axis, we're going to go up just a 1/2. So vertex, focus right above it. By the way, down a 1/2 to the directrix down here, correct? And then on either side of the focus, we're going to go over just 1. So our lattice rectum is a full length of 2. And then it's something like that, a much tighter parabola than what we'd seen in the past. Did we get something like this for the second one in the homework? All right, questions on that? Questions? All right, go and set up a new Cartesian plane on your graph paper. I'll give you just a couple more before we get into our new material today. Set up a new Cartesian plane on your graph paper. Let's do a couple more of these for extra practice. Now we've had a chance to see the homework and work through it. check your first.
For some reason I had it going to the left.
You get it going backward. Do you see that there's not a negative, so not backward. Negative either means backward or downward.
Right.
Here it goes forward. Okay, other than that, good? Good to go. Well, the next one, 0, 0, this time y-axis. Now this time there is a negative. It's going to be negative 1.5, and then 3 to either side here. So we're going to start at the vertex here, but we're going to go down 1.5, and then out 3 in each direction. Like that, and then of course we go down at 1.5, so we go up 1.5 to the directrix there. And how do we do on the second one? Good to go on that one. All right, questions at all on the basic easy parabolas? All right. By the way, real quick note, make sure these sides always keep spreading outward, 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 never coming parallel to each other. Right? Don't make a U, but keep that shape going out as we draw. All right, next thing in your notes, just as a circle can have its origin or its center move, right? We didn't keep all of our circles centered at 0, 0. No more will we keep all of our parabolas tied to 0, 0 as the vertex point. That parabola certainly can shift. Now, of course, if you remember back to Algebra 2, we talked about all of this in Algebra 2, and we had one method of approaching it, but we never got into lattice rectum length and things like that, right? We were still doing somewhat of a point-by-point plotting. Again, the point of analytic geometry is to free you from a lot, if not all of that. So next thing in your notes, translated vertex / origin. Translated vertex / origin. One way to think of this, and some textbooks will use this, is you're translating the origin, so therefore the vertex moves with it. Another way to look at it is you just move the vertex. There are two forms of a parabola with a translated vertex. Either x minus x1 squared equals 4py minus y1, or y minus y1 squared equals 4p x minus x1. And as you look at it, you're like, oh, I see what you did there, right? Just like for a circle, x squared plus y squared equals r squared versus x minus x1 squared plus y minus y1 squared equals r squared, right? They're both circles. This one's centered at the origin, this one's centered somewhere else, and the center translates to x1, y1. We'll have a parabola, but it's an x squared equals 4py or y squared equals 4p, y squared equals 4px. It's possible that x1, y1 is translated the vertex for us. Seem to make sense? All right, so some things to note here, and this is relatively, I think, common sense to you, but let's write it anyway. The vertex is no longer 0, 0, but x1, y1. The axis of symmetry is still going to be the non-squared variable. The focal length is still going to be p, and each side of the lattice rectum is going to be the absolute value of 2p. So the only thing really that's changing here is our vertex is moving. Everything else is going to stay exactly the same. Make sense? So then, write this one down, and we're going to graph it here in just a moment. X minus 3 squared equals negative 8 times y plus 1. X negative 3 squared equals negative 8 times y plus 1. Well, where's the vertex of this parabola? By the way, notice only one thing is squared. Only the x entity is being squared. The y entity is not. Okay, so that's how we know parabola, right? Where's the vertex?
3, negative 1.
3, negative 1. Which axis is the axis of symmetry?
Y.
What's the focal length of this particular parabola?
-2.
Good. Remember, the coefficient of the quantity is the 4p. So therefore, p is a -2. And then finally, each side of the lattice rectum is going to be how long? 4. Double this, but minus the sign, or half that, but minus the sign. So go ahead and set up a new Cartesian plane on your graph paper. Show you how I recommend you graph this. Bless you, by the way. First things first, plot your vertex, but instead of putting it at 0, 0, put it at 3, negative 1, right here in the 4th quadrant. My recommendation is to draw a new axis of symmetry. It'll help you to focus on what's going on. So we're going to draw, just real lightly, a y prime axis. If it had been x-axis of symmetry, I would have drawn an x prime axis instead. So I'm going to redraw just real lightly, no arrowheads on it. It's just for reference. And when you label it, make sure we label it y prime, because it's not the y axis, it's the y prime axis. It's an extra little axis for us. That's a big graph grid. Then on this Cartesian plane, from this vertex that we've plotted, on the axis that we drew, we're going to go, class, down 2. If it had been side to side, we would have gone backward 2. But we're going to go down 2. And if we go down 2 from vertex to focus, then we'd have to go up 2 from vertex to directrix. And then parallel to the directrix that we drew, through the focus, or from the focus, we're going to go out 4 in both directions. 4 here. 4 here to the endpoints of the lattice rectum. And again, just a nice gradual curve. Keep it going outward, not hooking into a super tight U shape. You should get something like this for our parabola. And let it go out a little bit more. A good test, and again, I'm not going to be too much of a stickler here unless it's really bad, but pick a random point. I'm going to take this point here, for instance. How many units away is this point from the directrix? Looks like 6. We got 6 units away. All right, so this is 6 units. Does that look like 6 units? I know you can't really measure it exactly, but does it look pretty close to 6 units? Good. But if I've curved my parabola in too far, like this, do you see that this and this aren't going to look as similar, right? So careful, again, it's kind of an eyeball thing. You're not going to test every single point, or if I've gone into just like straight lining, okay, that should also not happen. So we want to avoid 2 extremes. One is kind of curving in almost where I'm going to start going parallel. The other is kind of straight lining. We want to just keep a nice smooth curve going here. Questions on that example? All right, let's do another one. And you might be able to use the same Cartesian plane. I'm not sure I can, now that I drew all that. Especially Jamie, since you've got such a big one, nice one you've spent so much time on. Hate to go give a new one for you. Write this one down if you would, please. Y plus 2 squared equals 4 times x plus 5. See what I'm going to do? I'm going to try to save this. I'm going to try just taking the extra markings off. I'm not sure, this might be more work than it's saving. Okay, I'll take it down. It's like I always say, you lose some, you'll lose some. All right. It's a real positive strategy in life. That's what you call casino mentality. You lose some, you lose some. Clearly not advocating for casinos. If you haven't already, you might have worked ahead of me here. Go ahead and do your analysis. Vertex, axis of symmetry, focal length, and each side of the lattice rectum. I was right. Quentin had already done all of it, and as had Jamie. So if you haven't and you're watching on YouTube, pause for a minute, but they're already done. What is the vertex, Jamie?
Oh, when I went back to 0, 0, 0.
Oh, no, it's not 0, 0, right?
-2,
The fact that there's
-5.
x1s, y1s means it's not.
-2, -5.
Now here's where we have to be oh so careful with the parabola.
Oh.
This is y1, or negative y1. This is negative x1. And it's really easy to mess that up because we are used to seeing x before y, x before y. Well here, because the squared goes on one side, the non-squared the other, you can get them reversed if you're not careful. So,
It's -5, -2.
-5, -2. Really easy mistake to make. You gotta be careful with the parabola. Now, none of the other conics are like this. The ellipse is like the circle, x then y. The hyperbola is like the circle, x then y. It's only this guy. Just this one, which makes it that much harder, frankly. All right, which axis is the axis of symmetry for redemption?
X.
The x-axis. And what's the focal length?
1.
1. So each side of the lattice rectum then, Quentin, is 2. All right, so again, we're going to start by plotting our vertex. Right here in the third quadrant. Then I recommend you draw your axis of symmetry very lightly. So we're going to draw a new x-axis or an x-prime axis. Just real lightly here. Again, don't put arrowheads on it. It's not the axis, it's an extra axis. An extra axis. It's a lot of x's. On this x-axis, from my vertex, I need to go
to the right.
And the reason you draw the axis is you don't go up, right? That axis, by drawing it, it forces you to keep your eye moving sideways. Whereas in the last one, we wanted our eye going up and down. All right, we're going to go sideways 1 positively. And of course, if we go positive 1 to the focus, we need to go
-1.
backward 1 to the directrix. And then perpendicular to my x prime axis, parallel to the directrix I drew, I need to go up and down 2 from that focal point. So up 2, right, you're on the x-axis, and then down 2 here to the endpoints of the lattice rectum. And draw a nice smooth curve. Nice smooth curve. And get something like that. By the way, the less you draw, the better, right? If I just keep drawing and drawing, I'm probably going to mess up the way the curve looks. So I prefer not to draw super long. Okay, less is more. Less is easier, so I don't usually draw it super long. I'm not trying to fill up my graph grid necessarily. But there we go, something like that. All right, questions on this? Questions on this? All right, well, in our next lesson, we're going to kind of do like we did with the circle. We're going to go from the conic form into this parabolic form. So a lot of the algebra steps are going to be similar, but this evening, no homework. And so hope you have a wonderful rest of your day.